G'day, here's a straight line path. It's very straight, it doesn't bend at all. In fact, let me bend the line, let me put a kink in it. Let's draw it again, but then when I get to this point, instead of going straight, let me kink off, let's bend off at say an angle of 45 degrees. Great, that line is no longer straight, it's bent. In fact, let me give a measure of the bendiness right there at that point, at that kink. Bendiness. Let me define that to be the amount of angle I turned, which was 45 degrees, out of a full 360 I could have turned. That is, I turned 1/8 of a full turn right there. So I'm going to say the bendiness of that kink is 1/8 of a full turn. Grand! In fact, I'm having fun. Let's keep kinking this line. Let's keep bending it in such a way that I eventually end up going all the way back to start. That is, this time I'll be following a path that I guess is the outline of a polygon. There, 1, 2, 3, 4, 5, 6, 7. I think I did 7 sides then. All right, so there's a 7-sided path. Any number of sides is fine. So let's see if I can work out the total bendiness of this. All right, so to work out the total bendiness of that polygonal path, what do I need to do? Well, I need to look at the angle I turned at each kink. So there's an angle alpha 1 I turned, there's an angle alpha 2 I turned, I also turned an angle alpha 3, another angle alpha 4, alpha 5, alpha 6, and alpha 7. All right, so there's 7 angles like this. And I look at this and think, oh, I know something about these angles. Because from my school geometry days, it looks like I've just drawn the exterior angles of a polygon. And I know from my school geometry, the exterior angles of a polygon always add up to 360 degrees. The angle alpha 1 plus the angle alpha 2 plus the angle alpha 3 plus alpha 4 plus alpha 5 plus alpha 6 plus alpha 7, all 7 exterior angles in this picture must add up to 1 full turn, 360 degrees. High school geometry, great. In fact, I can kind of see it's intuitively true by playing with a marker. For example, let me place a marker here and actually apply that amount of turning to it, angle alpha 1. Here goes, zoom, great. Now let me slide the marker up here and now add angle alpha 2 amount of turning to that marker, zoom. So the marker's gone through that amount of turning plus that amount of turning. Let me slide over here and now apply this amount of turning to it as well. Boom. Then I add a 4th amount of turning to it, zoom. Then I add a 5th amount of turning to it, zoom. Add the 6th amount of turning and the 7th amount of turning and bring it back to start for comparison. And I can see that marker is now facing the same direction it was before. It underwent 1 full turn of turning, 360 degrees. Great, great, great. But remember, we measure the bendiness at each kink to be an angle out of 360. So the total bendiness of this polygon right here will be the first angle out of 360 plus the second angle out of 360 plus the third angle out of 360 all the way up to the 7th angle out of 360, which of course may add up to 360 out of 360 adds up to 1. The total bendiness of this polygon right here is 1 full turn. And in fact, there's nothing special about being 7-sided. It could be 700-sided polygon. The exterior angles will always add up to 360 degrees, in which case the total bendiness is again 1. Or 7,007-sided polygon. The exterior angles add up to 360 degrees, in which case its total bendiness is always 1. Grand, grand, grand. So the key fact about high school geometry is the exterior angles always add up to 360 degrees in a polygon. But let me really focus on that school geometry. Why do we say that? What makes us want to believe the exterior angles always add up to 360? I know my intuition says that. So what is it about school geometry that we believe that leads to that result mathematically? Let's focus on that for a moment. School geometry is all about figures and shapes and lines and so forth drawn on a nice flat planar surface. It's about flat geometry, which is really called Euclidean geometry today because some 2,300 years ago, the great geometer Euclid created a list of basic axioms, basic beliefs about how geometry should behave in a nice flat plane, Euclidean geometry. And one of the first most fundamental consequences of axioms is the following. It's about angles in a triangle. In Euclidean geometry, you learn that the 3 angles of any triangle you draw into the plane are sure to have the following property. These 3 interior angles are guaranteed to add to 180 degrees. In a planar flat triangle drawn on a nice flat plane, the 3 interior angles add to 180 degrees, a fundamental property of flat geometry. Which is great because now I can extend this result to other polygons. For example, here's a 4-sided shape, 1, 2, 3, 4. And I can see I can divide it into 2 triangles. In which case, in Euclidean geometry, the three interior angles of the upper triangle are sure to add to 180 degrees, and the three interior angles of the lower triangle are sure to add to 180 degrees. In which case, we can now see that the four interior angles of the original quadrilateral are sure to add up to two copies of 180 degrees, 360 degrees. Or if I draw a five-sided polygon, 1, 2, 3, 4, 5, I can see we can subdivide into three triangles. 3 is 2 less than 5. There's always 2 less. And the angles here add to 180 degrees. Angles here add to 180 degrees. Angle here add up to 180 degrees. Fundamental belief of flat geometry. And I can say that, oh, the 5 interior angles of the original 5-sided shape add up to 3 copies of 180 degrees, 540 degrees. And in general, draw an n-sided polygon. It will subdivide into n minus 2 triangles, in which case the interior angles of an n-sided polygon sum to n minus 2 times 180 degrees. Grand, grand, grand. But that's the result about the interior angles. We were talking about earlier about the exterior angles of a polygon. So let me talk about exterior angles now. How does that follow as a consequence of this basic belief from Euclidean geometry? All right, so let me draw a 5-sided shape. I'll just do a nice simple polygon for myself. 1, 2, 3, 4, 5. So we know the interior angles sum to, this will be 5-sided chops into 3 triangles, sum to 3 times 180 degrees. Great. So that's an interior angle beta 1, beta 2, beta 3, beta 4, beta 5. The reason I call them betas is because earlier we called the exterior angles alphas. Alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. Great. So we know that the sum of the betas, beta 1 plus beta 2 plus beta 3 plus beta 4 plus beta 5, is 3 times 180 degrees. Grand, grand, grand. But we want to know about the sum of the exterior angles, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 plus alpha 5. Okay, here goes. I can do it. I can prove it 360 as follows. First of all, note that alpha 1 plus beta 1, is actually on a straight line. So that must be 180 degrees. And alpha 2 plus beta 2 is also on a straight line. That's 180 degrees. Alpha 3 plus beta 3 is also 180 degrees. Yep. Beta 4 and alpha 4. Alpha 4 plus beta 4 is 180 degrees. Alpha 5 and beta 5. Alpha 5 plus beta 5 is 180 degrees. That's all true. Now let me add up all those equations. Let me add them all up. Okay, so let's see what I've got here. It's going to get a bit crazy. Right there, if I add up all the alphas, let me just write sigma, capital Greek letter sigma for S, the sum of all the alphas, alpha 1, alpha 2 plus alpha 3 plus alpha 4, plus the sum of all the betas, beta i's, would equal 180 plus 180 plus 180 plus 180 plus 180, 5 copies of 180. Oh, but the sum of all the betas is 3 copies of 180. This is 3 copies of 180. I can now deduce right now that this must be 2 copies of 180 degrees. It must be 360 degrees. The thing is, there's nothing special about 5-ness here. That if I did an n-sided polygon, how would this change? Well, the interior angles are summed to n minus 2 180 degrees. We can divide this n-sided polygon into 2 less triangles, n minus 2 triangles. So beta 1 plus beta 2 all the way up to beta n would add up to n minus 2 copies of 180 degrees. I still have that alpha 1 plus beta 1 is 180 degrees. Alpha 2 plus beta 2, blah, blah, 180 degrees, all the way down to the nth one. The nth one will still be 180 degrees. Right now, if I add up all these individual equations, the sum of all the exterior angles plus the sum of all the interior angles would be n copies of 180 degrees, because I'm doing this in an n-sided shape now. But I know the interior angles actually add up to n minus 2. N minus 2 180 degrees. So something plus n minus 2 180 degrees adds up to n 180 degrees. This must be 2 180 degrees. The exterior angles of any polygon in Euclidean geometry, in flat geometry, must indeed add to 360 degrees. That's what's going on. That's the mathematical logic behind flat space that says the exterior angles are sure to add up to 360 degrees. Great, I need to know that. Okay, instead of paths on a plane, let's now talk about paths on a surface. For example, let me start drawing polygonal paths on the surface of a cube. And I'll start with an easy example. Let me just do a very simple triangular path on this front face of the cube. And you look at that and say, James, that's not very exciting. That's still really just a path on a flat surface, on the flat front face of that cube. That triangular path is nothing new. It's still going to have interior angles adding to 180 degrees. It's still going to have these exterior angles adding up to 360 degrees. And the total bending of this thing is still going to be 1. Nothing new and exciting there. Okay, not a very exciting example indeed. All right, so let me make it a little more interesting. Let me draw another triangular path, but one that does this time. Let's start with an edge here, and another edge that goes up over that edge of the cube to that point there, and a second edge up and over like that. All right, there is my more interesting example of a triangular path on the surface of a cube. All right, so what have I done there? What I've really done there is this sort of thing. I've actually just drawn a nice triangular shape on a flat surface, 2 squares that got bent over like that. So actually, this really is just a picture of another triangle on a flat surface. The flat surface had to get folded over. But my interior angles are still going to add to 180 degrees. My exterior angles will be just the exterior angles here, still add to 360 degrees, and the total bendiness would be 1. Okay, still not very interesting. Oh, though it does make me want to point one thing out. I mean, if I have a line here that actually is meant to be straight, I know it doesn't look straight in my picture, but it really is meant to be straight on, across this edge, which means the 2 angles across the edge have to be make a straight angle, 180 degrees. That means this angle here and this angle here add to 180 degrees. So to do a straight line over the edge of a cube, just make sure these 2 angles here add to 180 degrees, because that would indeed correspond to a straight line on this flat unfolded version of the 2 faces of the cube. Great, all right, that's good to know. All right, but I need to draw a more interesting triangle. So far, nothing new about my triangles on the surface of a cube. So let me erase this. I have to erase part of the edge, I'll redraw that. All right. My more interesting triangle is going to be this. I'm going to look at the midpoint of this edge of the cube, the midpoint here, and the midpoint there. So edge length, that's half the edge length, half the edge length, half the edge length. These 3 edge lengths are the same. And I'm going to connect this point to that point to that point. There is my new triangle on the surface of a cube. Now, can I work out its interior angles? Well, I can, because I can see actually just this part of the triangle is a flat triangle. That's actually isosceles. In fact, it's got a 90-degree angle there. It's all part of a cube. So 90 and must be 45 there, 45 there. Well, 45, 45, 90. Same thing about this portion of the triangle. This is a nice flat isosceles triangle, 45, 45, and 90, and 45, 45, and 90 for the top part of that triangle. Great. Oh, but now I can see the interior angles are interesting. Because look at the interior angles. 45 plus 45, that's 90. Plus a 45, 45, that's another 90. Plus 45 plus 45, that's another 90. The interior angles out to 3 90s. 270 degrees. Okay, things are now changing. The exterior angles, can we figure those out? All right. If this edge were to keep going over properly, remember that meant I need that 45-degree angle to match with the rest of 180 degrees over there. All of this would have to be 135. Well, I've got 45 of it there, which means I'm off by 90 degrees. 90 degrees plus 45 is 135. Yes, bingo. So the exterior angle right there is 90 degrees. Again, over here, if I were to go straight, there would be 45 there and 135 there. Must add up to 180. But I've already got 45 of it there. This must be the rest of it is 90 degrees. Again, the exterior angle there is 90 degrees. And the same token, if I were to go straight there, I'm going to be off by 90 degrees in what I actually do. So the 3 exterior angles sum to 270 degrees. 90 plus 90 plus 90. This is indeed interesting. And finally, the total bendiness would be, this exterior angle out of 360, that's a quarter. Whoops, not 1, it's a quarter. Plus a quarter. 90 out of 360 plus a quarter. 90 out of 360, it's 3/4. It's less than 1. The total bendiness is less than 1. Interesting. This is less bendy than a planar triangle. The total bendiness is less than 1, yet it still closes up on itself. Very curious. And why must that be happening? Well, it must be because of the geometry of the cube. I've finally done an interesting triangle that contains some interesting geometry. Look at the corner of the cube. It's kind of very much not flat there. It's affecting the total bendiness of my path. All right, so somehow the pointiness of that corner is affecting the bendiness of my path. So now I want to talk about the pointiness of corners of polyhedra. Okay, great, I'm excited. Okay, let me now talk about pointiness of points in polyhedra. For example, here's a cube, and let me focus on this point right there. It's got 3 square faces meeting to make that point. It's got a 90-degree corner there, a 90-degree corner there, and a 90-degree corner there. So it's got 3 90-degree angles around it. Now actually, it's pointy because it only has 3 90-degree angles around it. If it had 4 90-degree angles around it like this, 4 squares, 90 degrees, 90 degrees, 90 degrees, 90 degrees will make a full 360, making a nice flat figure. It's the fact that I took one of those 90 degrees away that creates some pointiness. This actually is missing 90 degrees, that's what's causing its pointiness. So actually, again, the number of angles that's missing from 360 degrees is a measure of its pointiness. So I'm going to say the pointiness here is how many degrees is missing from 360, namely it's missing 90 degrees out of that 360. So that is, it's missing 1/4 of a turn around that corner. It should be a full 360, make it flat. It's missing 90 degrees. So I declare the pointiness of that corner to be value 1/4. By the same token, this corner also has pointiness equal 1/4. This corner has pointiness 1/4, 1/4, 1/4. All the pointinesses of a cube are 1/4. But actually now I've done that, I actually play the same game with other shapes. For example, if I took a regular tetrahedron, 4 triangular faces making a 3-dimensional shape. Here goes. There we go. So it's nice equilateral triangles everywhere. Then I'm going to say, okay, what's the pointiness here? Well, what I'm going to do is look at how many angles there are around that point right now. There's a 60-degree angle right there from that face. There's a 60-degree angle around there from that face. And there's another 60-degree angle behind it from the third face. Well, that's only adding up to 180 degrees. To make it flat, it would need a full 360 degrees of angles around it. That would make it flat. It's missing 180 degrees of turning, in which case, the pointiness is how many angles it's missing out of 360. I would say that has a pointiness value of 1/2. And now we've got it, because in general, if I did any polyhedron, any strange 3-dimensional shape with flat faces, it could be crazy, something crazy. How do I draw crazy in a hurry? That's good enough, that's crazy enough. I would define the pointiness of any point here to be the number of degrees missing, number of degrees from 360 degrees missing from around it. So how's that for terrible handwriting? Let's call it x. Then the pointiness would be x degrees missing out of 360. Whatever that ratio is, that's the value of the pointiness. All right, so somehow the degrees of pointiness of each corner is actually having some effect on total bendiness of paths around that corner. In fact, I bet the degrees of pointiness around several corners is going to have combined effect on the total bendiness of paths that closes them. Oh, let's explore that next. This is going to be interesting. Okay, so now I'm going crazy. What I've drawn here is a great big blobby polyhedron, some irregular thing, and on it I've drawn a nice polygonal path. Let's say it has n edges, so a path with n edges on my polyhedron. So if there's n edges, it also has n corners. There's a path with n vertices on it. Okay, great. But actually, so I can really identify the flat parts of this. So for example, I can see this is a little flat surface with a part of the boundary of my path. Let me actually include these crossover points as vertices on my path. So I'm actually increasing the number of edges. I'm also increasing the number of vertices, but let me include those. And I will be including counting exterior angles for the total bendiness, but they won't have any effect because right now this really is a straight edge. That'll be 180 degrees and that'll be an exterior angle of 0 degrees. So I'm not actually changing the sum of the exterior angles by including those points as part of my polygon. All right, so we'll say we now have a polygonal path of n edges and n vertices where every point like this is now a vertex. So now I've got a flat face there, and a flat face there, and a flat face there, and a flat face there. I've got all these flat faces. Great, because now I'm going to play with the angles in these flat faces because I want to get to the sum of the exterior angles for the total bendiness. And the way to do that is to do what I did before, is go through understanding the interior angles first. All right, okay. But, I know there's going to be subtleties here because we've got these inside points, these interior points here that are corners of the polyhedron. They have some pointiness. There's some pointiness to them, and that's going to affect, I bet, the total bendiness of that path. So the pointiness of those corners of the polyhedron on the inside of the polygon are going to cause us some interesting trouble. All right, so let's just get some notation here. So we've got n edges, a path with n edges. We'll say that. We'll let I equal the number of inside points, which are the corners of the polyhedron. They're going to cause some interesting trouble. What else should I measure here? Oh, I do want the exterior angles and the interior angles. So we'll let alpha 1, we can't even read that. We'll work out all these exterior angles. Some of them are 0, but exterior angles, all these exterior angles, alpha 1, alpha 2, alpha 3, alpha 4, blah, 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 up to alpha n, because there's going to be n of them. Let alpha I equal the ith exterior angle. We want the sum of the exterior angles, and then divide by 360, and that'll be the total bendiness. But with each exterior angle, there's an interior angle. So let beta I be the ith interior angle. All right, so far so good. This is a crazy picture. Let's see, I've got n outside vertices, outside edges. I've got I inside points here with the pointiness of the polyhedron, sorry. I've got I exterior angles, alpha 1, alpha 2, and so forth. Beta I interior angles, beta 1, beta 2, beta 3, so forth. Great. I do know that an exterior angle plus an interior angle is shorted out to 180 degrees. I know that's true. In fact, if I sum all the exterior angles and sum all the interior angles, I'll get the sum of a bunch of 180 degrees. I'll get n 180 degrees. So actually, I know the sum of all the exterior angles plus the sum of all the interior angles will be n times 180 degrees. All right, haven't actually done anything yet, but that's the situation I'm dealing with. What I might do, I might redraw this picture, but I don't need any of this outside stuff. All I'm doing is focusing on the path I've got there and all the inside pointy bits. They're the things going to affect stuff. So really this is the picture I'm looking at. And what I might do is just pause and draw a sort of a neater version of this so I can see what's going on, because that's a bit crammed. Back in a moment. Okay, I've made my board a bit neater. So I've got my polygonal path drawn on my polyhedron, but I've erased all the outside stuff. It's left the inside part. This is really three-dimensional. It's part of the polyhedron still bulging out at us. So I've got all these pointy corners right here at the polyhedron inside my path. I've got my path divided into flat faces. There they are. I've also, on occasion, taken a straight edge and actually put an extra point there, which is the edge of the polyhedron, which is not going to affect matters, because I want to know the total bendiness of this path, which is really about the sum of the exterior angles. So by me adding an extra vertex there, no worries, the exterior angle is 0. 0, it won't affect the sum I'm interested in. It does affect the number of interior angles, the angles of the interior, because there's 180 degrees there interior, but I've also affected the number of sides I've added. So actually these might change by doing that little feature there, putting points at the straight edges across the edges of the polyhedron, but it doesn't actually alter the particular sum I'm interested in. All right, so given that, I'm going to say there are n vertices, n edges for my polygonal path. I'm going to say there's I interior pointy bits, and I've got exterior angles alpha I, interior angles beta I. Alpha I plus beta I adds up to 180 degrees. So the sum of all the alpha I's plus the sum of all the beta I's is doing 180 degrees n times. Got it, that's where we were. All right, so our challenge is to get to the sum of the exterior angles of our path, the total bendiness. That will give us that. But the way to do that is actually go through the interior angles of what we've got. So I'm going to work out the interior angles of everything I see. What do I see? Well, I see triangular faces. There's some triangular faces. 180 degrees right there, 180 degrees right there in those three angles. Oh, but I'm counting a bit much. There's a four-sided shape. There's going to be two lots of 180 degrees. There's 180 degrees, two lots of 180 degrees, and so on. So actually, I could start adding up all the angles I see in this figure. That'd be fine. 180 degrees for each triangle, two lots of 180 degrees for each quadrilateral, three lots of 180 degrees for each five-sided shape, and so on and so on and so on. It gives us a bit too many angles, but I'll worry about that in a moment. Worry about that in a moment. So for notation, let F3 equal the number of triangular faces, and F4 equal the number of quadrilateral faces, and let F5 equal the number of five-sided faces, and so on and so on. As I said, each triangular face gives me angles adding to 180 degrees. Each quadrilateral face gives me angles adding up to 360 degrees, 2 lots of 180. Each 5-sided face, do I have any here? Oh, don't have any here, but okay, no worries. If I had any, it'd be 3 lots of 180 degrees, and so on and so on and so on. So I can see now that the sum of all angles, it's too many, all angles inside the path is going to be given by this. 180 degrees, F3 times. If I've got F3 triangles, I get F3 lots of 180 degrees. Plus 2 lots of 180 degrees, F4 times. 2 lots of 180 degrees, F4 times. Plus 3 lots of 180 degrees, F5 times, and so on and so on and so on. So the sum of all the angles inside my path is given by that formula. But that is really too many angles, too many angles. I've done that angle, and that angle. I've done that angle, that angle, that angle, and that angle. This angle, this angle, this angle. This angle, this angle, this angle, this angle, so on. And I've even got this angle, this angle, this angle, this one, and this one, and this one. In fact, I can see, yes, I will build up and get all the interior angles I want, but I'm getting all these extra angles around the corners of my polyhedron. I don't want those in my sum. I just want the sum of the interior angles, all this outside stuff, none of the inside stuff. So I need to subtract away the sum of all the angles around each pointy part of my polyhedron. Okay, I can do that. I can do that. So let me clean the board again and give myself some more space. Here goes. Back in a moment. Okay, so I wrote things a smidgen more neatly right there. So the sum of all the inside angles of my polygonal path is given by this crazy formula right now. But I don't want all the angles around the pointy points of the polyhedron within that path. So I need to subtract all those angles, and all those angles, and all those angles, all those angles, all those angles to get to the part of the formula right there, the sum of the interior angles. Okay, we can do that because moments ago we defined the pointiness of a corner of a polyhedron as follows. If I call the pointiness P, but I'll make this the pointer of the ith one. Looks like I've got 1, 2, 3, 4, 5 of them here. I interior points, I've got 5, I equals 5. So the ith one has pointiness given by the number of angles, degrees that's missing around 360 divided by 360. So remember the cube was actually missing 90 degrees. It's missing 90 degrees right there. So I had pointiness of 90 out of 360, 1/4. All right, great. So the pointiness actually tells me the number of degrees that are missing from around a corner. So that tells me x must be 360 times the pointiness of that ith corner of the polyhedron, which means that's the number of angles missing. So it means the number of angles actually there are angles around ith corner must be 360 minus what's missing, 360 pi. So there's a general formula for the sum of the angles around the ith corner inside the polygonal path. But I'll do that for the first one, plus do that for the second one, plus do that for the third one, plus the fourth one, plus the fifth one. So actually I want the sum of these over all I interior points. So that's going to give me a formula. Here goes, I can do it. Sum of all, okay, this is pretty bad, really inside points. The really inside, like these ones, sum of all really inside angles equals this first one, 360 minus 360 P1, plus 360 minus 360 P2, all the angles around there, plus 360 minus 360 P3, all the way down to plus 360 minus 360 Pi, capital I, the ith one. So sum all those up, I'll get I groups of 360, I groups of 360, minus 360 times the sum of all the pointiness. The total pointiness, the sum of all the pointiness. The pointiness there, plus the pointiness there, plus the pointiness there, plus the pointiness there, plus the pointiness there. So, bad board technique. Write this a little more neatly. The sum of all the really inside angles turns out to equal I times 360 minus 360 times the sum of all the pointiness inside the polygon. Bingo, bingo. So now I can start writing a formula for the sum of the interior angles, because it would be all the inside angles, take away all the really inside angles, will do the trick. Here goes. I'm excited because I can write that down. I now know the sum of the interior angles is going to be this formula, 180 F3 plus 2 lots of 180 F4 plus 3 lots of 180 F5 and so on forever. Take away 360 I's plus 360 I would call that the total pointiness inside the polygon. Total pointiness. The point is there plus the total point is there plus all the pointinesses. The total pointiness. So there is a formula for the sum of the interior angles, and it's truly horrid. What is that? That's a mess. That's a mess. In fact, this part is the worst. That part's the worst. I mean, total pointiness sounds good. Number of interior points sounds good. That thing, no idea what it really is. All right, so let's now focus on that thing. Okay, back in a moment. Okay, so here's what we have so far. I've taken out a common factor of 180, but we have that the sum of the interior angles of this polygonal path is 180 times f3 plus 2 f4s plus 3 f5s plus 4 f6 and so on and so on and so on. That strange sum minus 360 times the number inside points. I can make sense of that. Plus 360 times the total pointiness of those inside points. I can make sense of that. It's just this part is meaningless to me. I don't know what this stuff is. What is this stuff? Well, some of it I can make sense of. For example, I do know, for example, that f3 is the number of triangular faces, plus f4 the number of quadrilateral faces, plus f5 the number of pentagonal faces, and so on. All that is just the total number of faces. Most people usually call that f, the total number of faces. So at least that sum, which is maybe somewhat related to that, I know. That's the total number of faces. It's just all this extra stuff, extra stuff. All right, so what have we done here? We've looked at triangular faces, we've talked about their angles, but the only thing I haven't talked about those is the number of edges. For example, each triangular face has 3 edges. Each quadrilateral face has 4 edges. Each 5-sided face has 5 sides, 5 edges. So actually, I do know this, that each triangle gives 3 edges. So I've got 3 edges f3 times. Each 4-sided shape gives 4 edges. I know that I've got 4 edges f4 times. 5-sided shapes get 5 edges. I get 5 edges f5 times, and so on. Is the total number of edges in the picture. Except it isn't. It's not quite right. Because this inside edge will get counted twice. It got counted when I counted the edge of this triangle, and also got counted when I counted the edge of this 4-sided shape. This edge also got counted twice. As an edge of this triangle when I was part of that calculation, and as part of this calculation as one of the edges of the 4-sided shape. So this is really double the number of edges. It really got every edge twice. Except it's not true. That's not quite right either. Because this outside edge didn't get counted twice. It got counted once here from this quadrilateral, but didn't get counted by something else. This edge didn't get counted twice. It got counted once by this triangular face as part of this calculation, but didn't get counted again. So actually it's not double edges, it's double all the edges, except I didn't double the number of outside edges, so I've doubled the number of outside edges, what I shouldn't have, so I need to take away a count of all the outside edges. There are n outside edges. Yes, so it's actually this, take away n. Take away n. So every inside edge, but all edges got counted doubled except for the outside edges. N of them didn't, so I'm going to compensate by subtracting n. All right, now, oh, that's not this though. Oh, that is something different again. Oh, except I can see, I've got this. I can actually get it to look like this, where it's 1 f3, 2 f4s, 3 f5s, 4 f6, by subtracting 2 f3s and 2 f4s and 2 f5s and so on and so on. That is, I'm really just subtracting 2 f's, 2 of those. And what will I have? I'll have a single f3 plus 2 f4s plus 3 f5s plus 4 f6 and so on would be 2 times the edges minus n minus 2f. There we go. Beautiful. All right, so now I know what this beastly thing is, so let me now rewrite that formula. Oh, golly gee, where am I going with this? I don't know where I'm going. I'm just following my nose, trying to make things sensible to my brain. Okay, so what have we got? The sum of the interior angles, beta I, is 180 times this formula. Twice the number of edges minus n minus twice the number of faces, minus 360 times the number of interior points, plus 360 times the total pointiness of inside that path. All right. Do I like this? I don't know. Actually, I'm seeing lots of 360s. Let me just write this out one more time. The sum of the interior edges is 360 times the number, sum of interior angles is 360 times the number of edges, minus 360 360 the number of faces, minus 360 the number of interior points, plus 360 times the total pointiness, minus 180n. That is annoying, 180n. All right, so where is this leading me? What can I do? I'm just fumbling my way through here. All right, let's see. 180n. 180n. It'd be nice if it was 360n. I don't know why, it just feels like it would be nice. All right. Let me, actually, I do kind of want 180n's around the place. Oh my gosh, okay, okay. I'm not worried about that. I think I do want a 180n floating around. In fact, maybe, let's start going for what I want. I want the sum of the interior edges. The sum of the interior angles, exterior angles. The sum of the exterior angles, I'm getting so excited, will be n times 180 minus that. Oh golly gee, here goes. N minus 360e plus 360f plus 360i minus 360 the total pointiness plus another 180n, 360n's. 360n's. Oh heavens. This is really nice. This is really nice. All right. I've got it. I have now that the sum of the exterior angles is given by 360, the common factor of 360 in everything. Let's see if I can fit in this little space. I've got an n plus an I, I've got a minus an e plus an f, and then I've got a minus a total pointiness. Whoa, I'm so excited, I'm tripping over. Because what's n plus I? I mean this minus e plus f. N was the number of the outside vertices, I is the number of inside points. Most people call that V, the number of vertices you've got in total. The sum of the exterior angles is 360 times V minus E plus F minus 360 times the total pointiness. Let me now work out the total bendiness, because that was each exterior angle divided by 360 added together. I now have a formula for the total bendiness of my polygonal path. I'm so thrilled. This is great. It just sort of fell into place. Here goes. Oh, James, stop erasing the board. I'm too excited. I need to see it written down in full. Divide everything by 360. Okay, I have now that the total bendiness of a polygonal path drawn on a polyhedron is given by V minus E plus F minus the total pointiness. That is, I'll have this famous formula from graph theory called Euler, the Euler characteristic. Euler characteristic. Whoa. The total bendiness will always be the Euler characteristic. I've got the number of vertices in the diagram minus the number of edges plus the number of faces minus the total pointiness inside that polygonal path. Here's the amazing thing. Draw a polygonal path on a cube or a polyhedron or some regular polyhedron that can be like, it's basically sphere-like. If I could fill it with air like a balloon, it will just blow up into a sphere. It turns out this value is always 1. Always 1. If you worked out the number of vertices in this very picture here, and you subtracted the number of edges in this very picture here, and you added in all the various faces in this picture here, you'll get the value 1. Whoa! I'll prove that as part of this video because I will not skimp on the maths here, but look what we've just shown. We've just shown the total bendiness, the total bendiness of any path on a polyhedron is 1, like it is for a plane, but is deficient by the total pointiness inside that shape. The total bendiness plus the total pointiness is always going to be equal to 1. Whoa, that is stellar. That's stellar. In fact, I've lost track of what I'm actually doing. I think I need to do some concrete examples. So let me just clean the board and let's play with this example and this theorem here and see that's actually true. By the way, welcome to the Gauss-Bonnet Theorem formula. Oh my goodness, I'm so excited I can't even speak either. All right, back in a moment. Let me clean the board. Okay, so here's the Gauss-Bonnet Theorem, at least for polyhedra. For any polygonal path on a polyhedron, the total bendiness of that path, so we've got a path that goes all the way around, the total bendiness of that path plus the total pointiness of the surface within that path is always sure to equal a fixed number. Namely, if you look within the path, count the number of vertices you see within there, the number of edges that you see within there, the number of faces, then V minus E plus F will be a particular number. Turns out to be the same number as the total bendiness plus the total pointiness. But what's even extra cool, if my polyhedron is actually sphere-like, like a cube is, if I imagine like this is made of rubber and I could like fill up the middle with more and more air and actually expand, I can imagine expanding that cube to a sphere. That's what I mean by sphere-like. Then I claim V minus E plus F is always 1. The total bendiness of any path on a sphere-like polyhedron plus the total pointiness within that path is sure to be the number 1 for those nice polyhedra. Wow, the angles of bendiness and pointiness add up to 1 full turn. Crazy. All right, so I promised concrete examples. Let's try it. So let's try that interesting triangle example I did earlier on. So that's the triangle that connected midpoints of 3 sides like follows. There and there and there. So I've got really 3 flat right isosceles triangles. So this is 45 here, and 45 there, and 45, and 45, 45. Not can anyone read my handwriting here, because I can't read it either. But there's all the interior angles. But I wanted the exterior angles for total bendiness. If I remember correctly, if I was coming up this way, it's 45 there. I should go straight at 135 degrees on the other side, but I don't. I'm off by 90. If I remember, the exterior angle was 90 degrees. Exterior angle here was actually also 90 degrees, and the exterior angle here was also 90 degrees, in which case the total bendiness I can now do would be the bendiness here, 90 out of 360, 1/4, plus the bendiness here, 90 out of 360, 1/4, plus the bendiness there, 90 out of 360, 1/4, a total of 3/4. Yes, that rings a bell. Great. But now I've got the total pointiness to add to this, the total pointiness of inside that curve. And the only pointy bit inside the curve is this point right here. If I recall correctly, the pointer is actually measured by how far off I'm being a flat 360 degrees around that point. 90 there, 90 there, 90. It's missing 90 degrees to make a flat 360. So the total pointiness there, it's just the pointiness as one point, is actually 90 out of 360, which is 1/4. And look at that. 3/4 plus 1/4 does indeed equal 1. Whoa, there it is. If I want to just double check myself, I don't quite believe that yet, I can actually work out V minus E plus F for this example. So let me do it. How many vertices am I dealing with for this path and its inside? I see I've just marked 4 vertices. How many edges? Well, the 3 of the triangle and 1, 2, 3 there. That makes edges being 6 in total. And the number of faces inside the region is 1, 2, 3. Faces is 3. V minus E is -2 plus 3 is 1. Yes, total bendiness plus total pointiness matches 1. Whoa, there it is, the Gauss-Bonnet formula happening. All right, so let's do another example. That's fun. Let me do a cube again, because since I know that's sphere-like. Or let me do a really interesting path. Let me do a path that bends all the way back and starts to a start, but actually has no bendiness at all. Total bendiness will be 0 in this example I'm about to do. Here goes. All right, there's my wonky cube. I'm going to start here. I'm going to walk a path that goes straight across one face parallel to an edge. So that meets at 90 degrees there, and then I'm going to actually keep going at 90 degrees over here, which again is going to be parallel to the edges. So no bendiness right there. Nothing, no bending happened along here, nor right there. Then I'll go over the next edge, turn at 90 degrees, and come down the back face, parallel to the edges, and then turn another 90 degrees and come along the bottom face, parallel to the edges. So, my picture's a bit wonky, but can you kind of see what I'm doing there? All right, so here's my path. Here's my path. Maybe I shouldn't do that in green. I should do that in orange. That's part of the picture of the orange. All right. Okay, so there I did it. I was actually doing no bendiness anywhere. The exterior angle there, if you like, is 0 degrees, and the exterior angle there is 0 degrees. So the total bendiness would be 0 out of 360 plus 0 out of 360 plus 0 out of 360 plus 0 out of 360, which is 0. Total bendiness of this path is 0. Now, I guess I kind of implied this half of the cube is going to be considered the inside, so I'll consider this the inside. So what's the total pointiness of inside this curve? Well, now I can see inside this curve I've got 4 pointy corners of the polyhedron, and for a cube, each corner has pointiness 1/4. So I've got 4 corners, each of pointiness 1/4. So the total pointiness is 4 1/4 is 1. Whoa, 0 plus 1 equals 1. There it again. So a sphere-like polyhedron, it's 1. And to double check me on the V minus E+F part, let's work out V for this. How many vertices am I talking about in this picture? So there's my path, has some vertices, there's some other vertices, there's 4 there, 1, 2, and 3, 4, so there's 8 vertices in total. Number of edges I'm dealing with in this picture is, for my path and all its inside, 1, 2, 3, 4 edges at the top, 1, 2, 3, 4 edges on the bottom, and I can see 4 vertical edges, makes a total of 12 edges. And how many faces am I dealing with? Top face, bottom face, front face, side face, back face. That's 5. Bingo. V plus F is 13, take away E, 13 take away 12, yes, it's 1. There it is, the Gauss-Bonnet formula in action. Wow, I love it. Okay, let me give you a sense of the general Gauss-Bonnet theorem. So we started off with a straight path and then we did a kink. So we bent the path. And in fact, we gave a measure to that bendiness right there by looking at the exterior angle and defined the bendiness of that kink right there to be alpha out of 360. That's exterior angle out of 360. What fraction of a turn we've turned at that kink. And then we kept going. And we imagined, okay, this path just keeps kinking at different places and eventually returns to start. And we actually measure the bendiness at each individual kink and define the total bendiness to be the sum of all the individual bendinesses. Bingo. Great. That's what we did. But then you can imagine, well, okay, this is a curve that just chooses to bend at finitely many discrete points. You can envision a curve that just keeps smoothly changing direction as it goes along, a nice smooth curve that continuously changes direction. And Gauss actually figured out a way to measure the bendiness at each individual point along a smooth curve. He actually did it, how much this curve keeps wanting to deviate from going straight, and gave a measure to it. And the symbol we use for that measure now at each individual point is a small k, But if I want to do the total bendiness, then I actually have to add up all these individual bendinesses right now. But now I'm not doing a sum of finitely many points, I'm doing a sum of some sense of a continuum of points, and people call that an integral. The integral of the bendiness, all the bendinesses at each individual point. That would be the total bendiness of a smooth curve. All right, so we'll be talking about smooth curves. The total bendiness is now an integral of the individual curvature of a curve. All right, got that. And then, okay, upper dimension. Let's go to the polyhedron part. We were talking about the pointiness of points on a polyhedron. So for a cube, for example, we actually figured out a corner like this and gave a measure of the pointiness of that. And then we added up all the pointinesses that we're interested in and got the total pointiness. However, you can also imagine doing a smooth version of a polyhedron. You get some sort of nice smooth surface. Let me do something strange like this. Okay, that's a good one. Then you put some holes in it. Put a hole there, another hole here. So there is a smooth surface. Now you can kind of see that, well, it's not really pointy. If it's all smooth, it's not really pointy, but there is a measure of curvature to it. Like in some sense you can say, this is curved, but in a very angular way. This is kind of curved in a very smooth way. And Gauss actually figured out a way to give it a measure to the curvature at each individual point on a smooth surface. Right there, he had a nice measure of curvature. Another point here, a measure of curvature, a measure of curvature. He figured out a way to actually measure curvature on a smooth surface. And here he used the capital letter K for the curvature at any particular point. Will be capital K this time. Great, great. So actually there's an analog of this curvature here on a smooth surface. And then you can actually do an integral and actually get the total curvature of the surface. Great. But we're talking about not the total curvature of the whole surface, we're actually talking about total curvature within a region defined by a path. So now let me draw a path on this surface. Here it goes, I'll draw this path. And it goes back behind maybe. Great. And I'm going to consider this the inside, this part the inside. Oh, there's a hole there, there's a hole there. All right, okay, so what's the general Gauss-Bonnet theorem? It says, okay, I can think of this path here, got it, and this region here on the surface, got it. By the way, most people tend to call the region M for some reason, just become the standard letter, and people call this the boundary of M, which they denote this way, the boundary of M. So my curve is the boundary of M, and that's the part of the surface M. Great. So it turns out that the total bendiness of the curve, the integral k over the boundary, that's my curve, plus the total pointiness within the boundary, so just integrating over the region M of my total curvature, capital K, is always sure to equal V minus E plus F. All right, there are no V's, there are no E's minus F's there. However, another amazing result, that if I were to cover this with little triangles everywhere, just approximate this by coverage of triangles, then I can work out a V for how many vertices I used, I can work out an E how many edges I used, and an F for how many triangles I used or faces I used, great, and get a number. This number turns out to be the same no matter what. It's called the Euler characteristic of M. People use the symbol chi of M. Here is the general Gauss-Bonnet theorem. That if I did the total curvature of a nice smooth curve on a surface, and I did the total bendiness of a nice smooth curve on a surface, and then did the total curvature over that surface, I'm sure to get the Euler characteristic of that portion of the surface. Whoa, 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 whoa. Except I'm not quite right, because what I've been doing is about fractions of a turn. I did everything about a fraction of one full turn. Gauss and so forth were actually thinking about, no, let's call one full turn 2 pi radian. So actually, this is the number of full turns you got. So in the theorem, if I'm using radian, the theorem actually usually appears as follows. That the total curvature of the boundary plus the total curvature within the boundary is sure to be 2 pi times the Euler characteristic of the region I'm talking about. Whoa, there's the general Gauss-Bonnet theorem, and you can see I've got my polygonal version is really actually a version of that. Great. So Gauss actually discovered this, I guess, in the early 1840s or so, but never really published it in a way that was very clear and obvious to one and all. And it wasn't until about 8 years later, in 1848, I think it was, that Bonnet actually published a special case of this famous theorem. So the names Gauss and Bonnet became attached to this particular theorem. So it's now known as the Gauss-Bonnet theorem, about how curves on surfaces relate to the curvature of the surface they enclose. Beautiful stuff. Okay, let me now talk about sphere-like polyhedra. I kept saying a cube is sphere-like. What do I really mean by that? So here's a cube, and imagine it's made of rubber, and I can somehow insert a straw in, say, one face, not really puncture it too much, but enough that I can actually blow air inside that cube right now and keep expanding it. You can imagine if I kept expanding this rubber, I could actually make it a sphere. I could blow it so much this becomes just a round sphere, and on it this edge will get a bit warped. It looks like this. Maybe this edge here looks like that. I'll sort of see the front face go like that, then maybe the back face will be over there, or sorry, there's the top face, and then I might have a face over here. I guess I got 3 edges coming out of each. Can you imagine seeing each of these 8 vertices will still be there on the sphere somewhere, 1, 2, 3, 4, 5, 6, 7, 8 on the back side, and each of these edges will be on the sphere. Everything's just warped. But here's something fun. Suppose I really do now actually puncture the sphere, puncture it right there. And let me just open up that rubber now. So let me open up that rubber. Let's start opening it up. You can see what I'm trying to do. It's really stretchy rubber. Open it up. I guess you can't see that part. Keep opening up, and I can actually imagine I can flatten this down to a flat disc. And then I would now see, I still see my 8 edges. It might be just all completely warped, but I might now see something like this. Whoops. I think I'm doing it correctly. I think that's still a cube with that top line open up, and I'm just like making this picture on this flat rubber disc. So that's what I mean by sphere-like. It's really a polyhedron that if I can imagine is made of rubber that I could puncture and open up and create a flat disc from it. Great. So really, all the vertices, edges, and faces I'm seeing here are really vertices, edges, and faces on a flat disc. Except one of my faces, which one? This one here got really open up to the outside stuff. There's all the outside stuff from that face up there, which was my top face. So here's another sphere-like polyhedron. I'm going to do the same thing. Now, we were talking about paths on a sphere-like polyhedron. So here's a path. It's going to go around, all the way around, does its thing. What I want to do now is do exactly the same thing I did there. Now I want to flatten this out into a nice flat rubber disc. So what I might do this time is puncture it on the bottom and flatten it out this way, because then I get a nice flat rubber disc, and then I'd get my polygonal path somewhere, and I get all this stuff on the inside, all these triangular faces, hectagonal faces, all the rest on the inside. And I know, actually, in my proof, in my work today, I erased the stuff on the outside, so I don't care about the stuff on the outside. I can see, for a sphere-like polyhedron, all my edges, my faces, and vertices and so forth, I could actually imagine being on a flat surface. Bingo! So there I've got a shape now that I'm interested in about all these vertices, edges, and faces on a flat surface. So my polyhedron was, to begin with, sphere-like, means I could puncture it and flatten it. That means I'm really dealing with a picture with V's and E's and F's on a flat surface. So I claim on a flat surface, any diagram of V and E's and F's is always going to satisfy this relationship. That's what I've been saying all along. All right, let me see if that's true. Let me play with that. And let me see if I can give a sort of a good reason why that's very likely to be true. All right, here goes. Having a hard time erasing. So what I'm really studying here are diagrams of some vertices. I'll just draw the vertices first. Here happens to be 7 vertices, I think I just did. V equals 7. Let me add some edges. I'm going to be crazy. In fact, I'll do crazy things on my edges. This doesn't happen in Polyhedra. I'll do an edge that goes back to itself. I'll do multiple edges for the same 2 vertices and so on like that. Great, there's a graph. Oh, actually, let me connect it up and make a region. Oh, let me make it not disconnect. Let's not have an isolated vertex. Let me do that. All right. All right, so what have I got here? Vertices was 7. I didn't change that. How many edges did I just draw? Uh-oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's just 1, 10. Edges is 10. And faces. Now remember I was ignoring the outside stuff before, so I guess I'm only counting the inside faces, the finite regions. 1, 2, 3, 4. Faces is 4. And look, V minus E is -3 plus 4 is 1. There it is. There it is. So I want to see if I can justify why these things, these graphs drawn with vertices, edges, and faces, always satisfies this. By the way, some people might be very surprised I'm saying 1 here, because some people say, no, you really should count the outside region as well. In which case, you are going to count the outside region. This goes up by 1, this goes up by 1, and people say should be 2. All right, so if you count the outside region, it's 2. If you count everything on that sphere, it's 2. But I was getting rid of 1, I punctured 1 face there, spread it out, became my outside region. I'm not counting outside regions, so I am 1 less than what some people expect. Anyhow, for us in this video, V minus E plus F equals 1 for graphs coming from sphere-like polyhedra. All right, I need to point something out. You saw me quickly correct myself by saying, no, let me draw an extra edge so it's not disconnected. Something goes wrong if I've got a disconnected picture. Let me show you a disconnected picture. Let's do this. I'll keep it simple. I'll do 3 vertices here, and I'll do 2 vertices there. I've got some graph there, and I've got some graph there. Now, I know I've got very small numbers here, but I know for this left graph, I've got some left number of vertices minus some left number of edges plus some left number of faces. I know this equals 1. For what I've just done. In fact, I can check it is. V and E, yes, it's 1. Here I've got on the right some right number of vertices minus some right number of edges plus some right number of faces will also be 1. However, if I consider this as one picture, one single picture, then the total number of vertices would be this, those 2 numbers added together, minus total number of edges would be those 2 numbers added together, plus total number of faces would be those 2 numbers added together, equals 1 plus 1 is 2. Not 1, it's 2. Well, that's actually because I added 2 individual formulas for each component. There are 2 components, I got 2. So actually, I claim this formula is this. V minus E plus F is C, where C is the number of pieces, number of components your picture has. That's what I want to prove. Now, we normally just draw pictures with 1 component, in which case C is 1. Great. But let me prove this general formula right now. For any set of vertices, faces, and edges on a plane, V minus E plus F is sure to equal C, where C is the number of components you have. All right. Okay, so here comes my pretty convincing argument. If you want to do really rigorous mathematics, you get very clear about the topology I'm talking about. But intuitively what I got, I think is pretty clear. All right, I'm going to have a picture of some vertices, faces, and edges. So let me just say, got your picture, get rid of all the edges. Just draw the vertices first, and we'll put the edges back in. So there's a picture with some vertices. So right now the number of vertices is 0. Is some number V. I've got no edges. The number of edges is 0. Number of faces, I'm not counting the big infinite one. Faces is 0. And the number of components is, Each individual vertex has its own component, so it's also V components. All right. Right now, V minus E plus F is V minus 0 plus 0. That's V on the left equals C, which is V on the right. My formula is working. So right now, my formula is working. Everything's good and balanced. Great, great, great. All right, now let me draw in an edge. What can happen if I start putting those edges back? Let me draw an edge here. All right, I'll go between two distinct vertices. So I've added one edge to the picture. So my number of edges has gone up by 1. But I connected two vertices. I connected them. I made the number of disconnected pieces, the number of components, go down by 1. They went down by 1. And look, without me even doing the counting, I know this has to be true. If E went up by 1, then I subtracted a 1 on the left, and I did subtract 1 on the right. This formula must remain balanced. That must still remain true. Great, great. My formula is still true. Let me put in another vertex. Let me do this. In fact, let me be sneaky. I'll put another edge. I'll put another edge like this. This time, I didn't make a new component. I stuck with the same component I was on. In fact, closed things up and made a face. I made a region. Okay, number of vertices hasn't changed. I did add an extra edge this time, but now I've created a face, but I didn't change the number of components. All right, look at this. My formula is still balanced. V minus E, that went up by 1, plus F, that went up by 1, so I've subtracted 1 and added 1, still has to be the same formula. I've changed nothing on the left-hand side, it must still be true. It's still balanced. Great. In fact, you can argue, every time I draw an edge, if I connect two pieces, components goes down by 1, edges goes up by 1, stays balanced. If I connect two pieces, components goes down by 1, edges go up by 1, same balanced formula. Create a region, number of regions goes up by 1, number of edges goes up by 1, still everything's balanced. Everything I do is balanced. If I do this, come back. If I create a region up by 1, but I did so by adding an edge, down plus 1 there, keeps balanced. All the motions you do to redraw your graph actually keeps this equation balanced. And if it's balanced for the disconnected vertices, that has to be balanced all the way around until I eventually create my original graph. So that must be true. This must be true for my original graph to begin with, until I've got one component, in which case C is now 1, and it must still be balanced and still be true. Oh, I think that does it. I think I've covered everything I can think of to say about the Gauss-Bonnet formula, at least for today. Thanks so much for watching and hanging in there. Yes, this is another long video. You're a hero for working your way all the way through it. I so appreciate it. All right, thanks so much.